Hello, my precious friends. I really hope that you are doing great. Welcome to today's class. It is our first lesson on the fifth topic of Form 4, which is called Electromagnetic Induction. As usual, let me commence by giving the quote of the day, which states that life will always give you a second chance called tomorrow. We shall discuss that quote at the end of our class today. So today we are looking at electromagnetic induction. So to understand this topic better, I'll advise you to go back and watch our videos on magnetic effect of the electric current, which is a chapter that we covered in Form 2. The reason being, this particular chapter, that is electromagnetic induction, requires prior knowledge from magnetic effect of an electric current, or in short, electromagnetic induction is simply a continuation of magnetic effect of an electric current. So to be in a better position to link up concepts, first of all, watch our videos on magnetic effect of an electric current. You'll be in a better position to understand this chapter better. Now, in Form 2, under a topic called magnetic effect of the electric current, which we covered in this particular channel, we said that a conductor carrying current has a magnetic field around it. Similarly, a changing magnetic field under suitable conditions can induce current in an electric conductor. So this phenomenon is what we call that is electromagnetic induction, which was first discovered by an English scientist by the name Michael Faraday, FRS, who made greater contributions in the study of electromagnetism and also electrochemistry. So he was the son of James Faraday and Margaret Faraday. So that's a brief history about the discovery of magnetic effect, that is electromagnetic induction. Now, in layman's language, electromagnetic induction refers to the process of producing electricity with the aid of a magnet and a conductor. That is the process of producing electricity with the aid or the help of a magnet and a conductor. So that means when you want to produce electricity, then the main apparatus that you need a strong magnet and of course a conductor and of course something to rotate that particular conductor. Now, an experiment to illustrate electromagnetic induction can be set up as shown below. So one, we can use what we call a straight conductor. You can see we have our straight conductor AB. We can also do the same experiment using what we call a coiled conductor. So this is our coiled conductor. So let's start by discussing electromagnetic induction by use of a straight conductor. The apparatus that you need a straight conductor AB. You also need a galvanometer, that is a center zero galvanometer, which actually its purpose is to detect any current or any EMF that has been induced in this particular conductor. Remember, the only difference between a galvanometer and an ammeter is that a galvanometer is able to detect small changes in current, and it is usually its scale always starts from the point 0, such that when there is no current flowing through the circuit connected to the galvanometer, then the pointer of the galvanometer will always be at the 0 mark. But when current flows through the circuit where a galvanometer is connected, then we expect a galvanometer either to deflect to the right or to the left hand direction, depending with the direction of that particular current. We also need some connecting wires and of course a U-shaped magnet, of course, which produces the magnetic fields. So remember, under the first topic of Form 2 work, which was magnetism, we did say that magnetic fields will always move from the North Pole towards the South Pole. So these are our magnetic fields. That is when we are looking at the properties of magnetic field lines. They always originate from the North Pole towards the South Pole. So to carry out this experiment, we actually place the conductor in between the magnetic field, whereby it is observed that when you move this particular conductor up and down, or in such a way that the conductor cuts the magnetic fields at an angle of 90 degrees, then we expect to see a deflection on the galvanometer. So a simple way of understanding how electricity is produced, just observe what we call the bicycle dynamo. So the bicycle dynamo, in that particular case, we usually rotate the magnet instead of the conductor. So in the bicycle dynamo, the magnet, we have a round magnet within it, which is usually rotates as the wheel of that particular bicycle also rotates. Then in that case, the conductor is the one which is made stationary. So the key point here is that the conductor has to meet the magnetic field lines at an angle of 90, yeah, in order for EMF to be induced. So for example, for the case of a bicycle dynamo, it has a round magnet such that as the wheel, that is as the tire of that particular bicycle rotates, that is when someone cycles the bicycle, the tire of the bicycle rotates, then it is connected in such a way that as the tire rotates, it also rotates the circular magnet within that particular bicycle dynamo. Then the circular magnet is placed or positioned in such a way that as it rotates, its magnetic fields cuts the conductor at an angle of 90. So whenever a conductor meets the magnetic field lines at an angle of 90, that is in a given rotation, then we expect some EMF or some current to be induced in that particular conductor. So when the conductor is moved up and down, that is perpendicular to the magnetic fields, the observation made is that we expect to see a deflection in the galvanometer. So the deflection in the galvanometer will be observed. That is, it is only observed when the conductor AB is moved up and down, or when the conductor AB is moved in such a way that it cuts the magnetic field lines at an angle of 90. So the observation is that the galvanometer deflects. Why does the galvanometer deflect? Because an EMF or a current has been induced in this particular straight conductor. So the deflection of the galvanometer indicates induction of EMF or current in the conductor AB. But when it is kept stationary, when you keep the straight conductor AB stationary, that is without moving it, or when you move it parallel to the magnetic fields. So remember, moving parallel simply means that moving the conductor AB from the left-hand direction towards the right-hand direction. In such a way, the conductor will be moving parallel to the magnetic field lines. So when the conductor is moved parallel to the magnetic field lines, it simply means that that particular conductor is not cutting, or it is not meeting with the magnetic field lines at an angle of 90. And we have said that EMF will only be induced, or current will be induced, whenever a conductor cuts the magnetic field lines at an angle of 90. So when you move the conductor parallel to the magnetic fields, or when you hold the conductor stationary, it means that that particular conductor is not cutting the magnetic field lines at an angle of 90, and therefore we do not expect any EMF or current to be induced, and that is why there won't be any deflection in the galvanometer observed. So when the straight conductor is kept stationary, or when it is moved parallel to the magnetic fields, it does not cut the magnetic field lines at an angle of 90, and therefore there will be no deflection observed in the galvanometer, showing that no current has been induced. Now, the same experiment can also be carried out using what we call a coiled conductor. So this is our coiled conductor. Then of course we connect it to the galvanometer to detect whether some current is being induced or not. We have said that a galvanometer usually has the pointer. When no current is passing through the galvanometer, its pointer is always at the 0 mark. Then its scale increases towards the right hand direction or in the clockwise direction. Then on the left hand direction or in the anti-clockwise direction, its scale reduces. So when current passes through this particular conductor, which is of course is in connection with the galvanometer, then we expect either the galvanometer to deflect to the right hand direction or to the left hand direction, depending with the direction of the current or EMF that has been induced. So we need also a magnet. So the key point here is that, remember, if this is a magnet, if this is our bar magnet, then we expect the magnetic field lines to be moving from the north pole towards the south pole, also downward from the north pole towards the south pole. So when you move this particular magnet, when you move it in and out of this particular solenoid or into this particular coiled conductor, then we expect the magnetic field lines of this particular bar magnet to interact or to cut the conductor with this particular conductor at an angle of 90. Remember, when you're moving the magnet in and out, the magnetic field lines are cutting because the conductor is moving up and down. That is, it is coiled in this particular manner. So when you move the magnet inside and outside of that particular solenoid, then the magnetic field lines will be meeting with the conductor at an angle of 90, and therefore in that particular case we expect some EMF or current to be induced. So when the magnet is kept stationary inside the coil, when you keep the magnet stationary, it is not interacting with the magnetic field lines at an angle of 90 because you are just holding it stationary. So when the magnet is kept stationary inside the coil, there is no deflection on the galvanometer. Why? Because there is no interaction between magnetic field lines and the conductor. Therefore, we do not expect any EMF to be induced. And when no EMF is induced, the deflection on the galvanometer won't be there, or the galvanometer will simply point to the 0 mark, indicating that no current or EMF has been induced. But if the magnet is moved in and out of this particular solenoid, when you move it in and out, that action of movement causes this coiled conductor to interact with the magnetic field lines of this particular magnet, of course at an angle of 90 or at right angles. So if it is moved in and out, the galvanometer deflects, showing that an EMF has been induced. So this shows that an EMF is induced in a conductor only if there is a relative motion between the conductor and the magnetic fields. And the relative motion, we mean that the movement has to be in such a way that the magnetic field lines meet with the conductor strictly at an angle of 90 or at right angles in order for maximum EMF or current to be induced. So the conductor causes the field to change, hence an EMF is induced or some current is induced. So the key thing to note whenever you are handling physics experiment, the key thing you need to know the expected observation and then the expected explanation. Observation is always based on the 5 senses. That is, it has to be either something you can see, something you can hear, something you can touch, something you can smell. Yeah, any observation has to be based on the 5 senses. For example, the observation made here is that when the conductor AB is moved up and down, or it is moved up and down within this particular magnetic field, the observation is that we expect a deflection in the galvanometer. Note that you are able to see when the pointer of the galvanometer deflects, but you cannot give an observation such as current will be induced in the conductor AB. You cannot see current. What you can see or what you can detect using your senses is an observation, that is seeing the deflection of the galvanometer. That is why if you are asked to give the expected observation, is that when the conductor is moved up and down or perpendicular to the magnetic field lines, the observation is that there will be a deflection in the galvanometer. So that is the observation. Then when the conductor is either moved parallel to the magnetic field lines or when it is kept stationary, the observation is that there won't be any deflection on the galvanometer. So that is the observation. So don't give an observation such as maybe the current will be induced in the conductor AB. You cannot see current being induced. What you can see is a deflection in the galvanometer, which indicates presence of current. Similarly, you'll be asked to explain or state the expected observation when the conductor or when the magnet is moved in and out of this particular solenoid or the coiled conductor. The observation is that the galvanometer will deflect. So that is what you are able to see using your senses, that is the eye. But you cannot say that the current will be induced in the conductor because you cannot see current. What you can see is the deflection. Then the other question is, you should be able to explain your observation. So why does the current or the EMF, or why does the galvanometer deflect? So the galvanometer deflects, showing that an EMF has been induced in the conductor. And the EMF will only be induced if there is a relative motion between the conductor and the magnetic fields. So the conductor causes the magnetic field to change, hence an EMF is induced. Next, we look at the factors that affect the magnitude of the induced EMF or the induced current. And the first factor is the strength of the magnet. So the stronger the magnetic field, the higher the induced EMF. Of course, when the magnet is strong, it is going to give us stronger magnetic fields or stronger magnetic fields. Yeah. Then when the magnetic field is strong, then it simply means that the induced EMF will be higher or the induced current will also be higher. So if you want to increase the induced EMF, you simply use a stronger magnet in this particular case, so that it gives you stronger magnetic field lines, which will lead to more induced current in this particular conductor. Same case here, you use a magnet which has stronger magnetic field lines, or which has a stronger magnetic field, such that the induced current will be more. Then the second factor is the number of turns of the coil, whereby you are saying that induced EMF increases with increase in the number of turns of the coil. Yeah, for example, in this particular case, you can see this is our coil. It has some turns here. For example, these are 1, 2, 3, 4, about 5 turns. So if you want the magnetic field lines, if you want the EMF induced to be more, you simply increase the number of turns of this particular coil. For example, apart from having 1, 2, 3, 4, 5 turns, you can maybe make, for example, 20 turns. So the more the number of turns of the coil, the more the EMF induced. So to increase the magnitude of induced EMF, you simply increase the number of turns of the coil, whereby you are saying that induced EMF increases with increase in the number of the turns of the coil. That is to say that induced EMF is directly proportional to the number of turns of the coil. Then the third factor is the nature of the core, whereby you are saying that induced EMF increases when a soft iron core is used. Yeah, this particular solenoid or this particular coiled conductor is usually placed on a core. So when we place it on a soft iron core, remember soft iron cores are easy to magnetize and easy to demagnetize. So that means when you'll be moving your magnet in and out of that particular core, then its ability to get magnetized and demagnetized will be very high as compared to, for example, something like steel, which is a hard magnetic material. So when you use a soft iron core, then we expect more EMF to be induced. The reason being, soft iron cores are easy to magnetize and demagnetize. Remember that process of magnetization and demagnetization, as the magnet actually interacts with the as the coil interacts with the magnetic field lines at an angle of 90, that is what leads to induction of the EMF or the current in that particular coil. Then the fourth and the last factor that affects the magnitude of induced EMF or the size of induced EMF is the speed at which the conductor is rotated or moved. For example, in this particular case, the conductor is being, we said that we move the conductor, or we rotate the conductor up and down, such that the conductor meets the magnetic field lines at an angle of 90. So the speed at which the conductor is rotated or moved, so this point can also be stated as the rate of change of the flux linkage. Yeah, you can either give the speed at which the conductor is rotated or moved, or you can also give this point as the rate of change of the flux linkage. So the induced EMF increases with increase in the relative speed of motion of the conductor in the magnetic field. So the faster you rotate this particular conductor within this magnetic field, the more the EMF that will be induced. Similarly, the faster you move this particular magnet in and out of this particular core, the more the EMF that will be induced. So the speed at which the conductor is rotated or moved, or the rate of change of the flux linkage, will always be directly proportional to the magnitude of the induced EMF. Now from this particular point, we obtain what we call the Faraday's law. That is from the name Michael Faraday, who actually made greater contributions to electromagnetism. So the Faraday's law of electromagnetic induction states that the magnitude of the induced EMF is directly proportional to the rate of change of the magnetic flux linkage. Remember, the rate of change of magnetic flux linkage simply means the rate of rotating that particular conductor within a magnetic field. So the magnitude of the induced EMF will be directly proportional to the rate of change of the magnetic flux linkage. So the induced EMF will be directly proportional to the magnitude of that is the rate. Whenever we talk of rate in physics, it means we are dividing by time. So the rate of change of the magnetic flux linkage. So the magnetic flux linkage divided by time. So in abbreviation, you can say EMF, the induced EMF, is directly proportional to the rate of change of magnetic flux linkage. So magnetic flux linkage is denoted by B. Then of course T stands for the rate of change in that particular case. So you shall further look at this particular equation that is at higher levels, that is beyond high school level. But for this this level, at least you need to know how to state the Faraday's law of electromagnetic induction, which states that the magnitude of the induced EMF is directly proportional to the rate of change of the magnetic flux linkage. So this one is simply to say that, in simple terms, we are simply saying that the speed at which the conductor is rotated is directly proportional to the EMF that will be induced, such that the faster the speed, the more the EMF that will be induced. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that life will always give you a second chance called tomorrow. So the quote is encouraging us not to give up on our long-term dreams whenever we encounter setbacks while trying to achieve our daily goals. Remember, the best way to achieve a dream is first of all to break it down into some small objectives that you can achieve each day. Then the quote is also is reminding us that each day is an opportunity for us to move closer to our goals and become better versions of ourselves. Recall that compound interest of small steps in the right direction is massive success. Therefore, ensure that you achieve something small each day. Remember, when you find the sum of those small daily achievements, then the end will be a massive success, which we are calling the compound interest. And lastly, remember that the probability of winning will always be zero if you don't give yourself a chance to try. Yeah, don't give up, just give it a try. If it works, well and good. If it doesn't work, you'll get the experience. You'll also learn something out of that particular difficult moment. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscribe button and also turn on the notification bell so that whenever I upload a new video, you'll get notified. Until next time, this is Kind Tuition Academy. Thank you very much.